Okay, so in this video, we will consider the following family of linear systems. Now, why do I say family? Well, let's look at the system closely. We have three equations and the three variables x, y, and z, but there is this k floating around in our linear system. Now here, k plays the role of a parameter. As we take on different values of k, we will be getting different linear systems. Let's consider two examples of this. If we take k to be, say, -1, then the linear system becomes x plus y minus z equals 1, x minus y plus 3z equals 2, and 2x plus 3y minus z equals 3. And so you see, if you replace k by -1, then you get this linear system. Well, if you replace k by, say, 4, you will get a different linear system. The first equation stays the same. The second equation becomes x plus 4y plus 3z is equal to 2. And the third equation becomes 2x plus 3y plus 4z. Is equal to 3. And so on. So for every different value of k that you choose, you will get a different linear system. Now there is a natural question to ask. How could we perhaps classify these linear systems according to values of k? Well, we know that a linear system always either has no solution, a unique solution, or an infinite number of solutions. So we could classify the linear systems in our family according to the values of k when we have no solution, a unique solution, or an infinite number of solutions. To do this, we have to try and row reduce the linear system, keeping k as a parameter, and keeping in mind two things. Which variables are free, which variables are leading, and then we have to watch for possible inconsistencies. That is, when there is a row of zero coefficients and a non-zero constant. So let's look at the corresponding augmented matrix and figure out how this will play out. Keep in mind that we don't really want to find the solutions. We simply want to count them. So it's enough to find what we will call potential leading ones, values that we could turn if we wanted to into a leading one, just so we can figure out if a variable is leading or free. So the first row, 1, 1, -1, 1. Second row, 1, k, 3, 2. Third row, 2, 3, k, 3. Alright, we already have a leading one in the top row. Let's use it to kill the two entries below it. So let's do row 2 minus row 1, and row 3 minus 2, row 1. We can recopy the first row as we're not changing it. Let's apply the first row operation. Row 2 minus row 1, so we get 0, k minus 1, 3 minus -1, 3 plus 1, 4, 2 minus 1, 1. The second row operation, so 2 minus 2, 0, 3 minus 2, 1, k minus 2 times -1, k plus 2, 3 minus 2 times 1, 3 minus 2 is 1. And so we have now our first leading one. We've killed the entries below. We ignore the top row, and we look for a second possible leading one. Well, the two entries here is 0, so we have to move on to the second column. There are two entries here. There's 1 and there's k minus 1. Now you have to be careful. You can't just simply be naive here and divide by k minus 1 across row 2 to get your second leading one, because k is allowed to range over all real numbers. And so if k equals 1, this entry is 0, and you cannot get a leading one from k minus 1 always. So you have to go with the safer choice of the 1 here, so we will simply swap row 2 and row 3. The lesson here is never divide by an expression in terms of k to construct a leading 1, as for certain values of k, that could be 0, which would mean that your operation is not valid. So here we go with the better option of swapping row 1 with row 2. Row 2 with row 3. So row 2 and row 3. So we have our second leading 1. So far, we know that for any value of k, x is always leading, y will always be leading. Well, let's continue our reduction. We have our second leading 1, let's kill the entry below it. Well, to kill k minus 1, we must do row 3. And now think of it, if this value was 4, we would do minus 4 row 2. If this value was 7, we would do minus 7 row 2. So we simply do minus k minus 1 row 2. Because k minus 1 minus k minus 1 times 1 is k minus 1 minus itself, which will end up being 0. Let's apply this row operation. As always, first let's recopy row 1 and row 2 as we're not changing them. We'll get 0, 0. And here let's perform these two last entries on the right hand side. So we have 4 minus, let's do it here, 4 minus k minus 1 times k plus 2. Let's multiply this out. 4 minus k squared plus 2k minus k plus k minus 2. Let's distribute. We'll have negative k squared negative k. 4 minus negative 2 is 4 plus 2, positive 6. We're going to ask, this will be the entry here, which will possibly be a third leading 1, only if it's not 0. So we'll have to figure out when this equation is equal to 0 and when it's not equal to 0. As it is a polynomial, it's a good bet to factor it. We'll factor the negative 1. We'll be left with k squared plus k minus 6. And now let's try the sum and product trick. Can we factor by inspection? The product would be negative 6, the sum would be positive 1. Well, this is negative 2, positive 3. K squared plus 2k minus plus 3k minus 2k is plus k minus 6, check. And so we have our entry here, the negative of this expression. So negative k minus 2 times k plus 3. And finally, 1 minus k minus 1 times 1. Let me do it here since I have the space. 1 minus k minus 1 times 1. So all we have is 1 minus this, which is minus k minus minus is plus, plus 1. And so we get 2 minus k. And now this is where things are interesting. We have reached the final row of our matrix. And so we are essentially done here with our reduction. Let me give this entry a name. Let's call this alpha. Well, there are really just two options. Either this entry is equal to 0, or it's not equal to 0. Now let's think of it this way. Let's start with this being not equal to 0. Think of what the consequence is. The variables were x, y, and z. Now if alpha, this entry, negative k minus 2 times k plus 3, is not equal to 0, then whatever it is, the next step is to divide by it, and this will become a third leading one. Suppose this entry was 5, multiply by 1 over 5, and z is leading. If the entry was 4.36, divide by 4.36, and z is also leading. So whatever the value of alpha is, if it's non-zero, divide by it, z is leading. But then, this implies that x, y, and z would be leading. But if all the variables are leading, our linear system has a unique solution. And we're done. So the only question left over, of course, is the second case. What if alpha is 0? Well, alpha is 0 if and only if it is factored right here, if k equals 2 or k equals negative 3. And so you see what we have is actually quite simple. For any value of k other than 2 and negative 3, alpha is non-zero, all the variables are leading, and we have a unique solution. Then we have two special cases, when k is 2 and when k is negative 3. Those are our last two special cases, and we have to check them one at a time. So let's check what happens when k equals 2. Plug it back in the reduced or the row echelon form of the matrix, see what we get. The first row stays the same as there is no k. The second row will become 0, 1, 4, 1. And the third row will become 0, 0, 0, and 0. So if you notice, x and y are leading. The bottom row is actually trivial. It says that 0 is equal to 0. So the system is consistent. But as z is free, and the linear system is consistent, we have a free variable, it will become a parameter, which implies that we will have an infinite number of solutions. And here I'll be lazy, I'll simply write infinitely many solutions. And that's it. So we figured out when k equals 2, the linear system has infinitely many solutions. Well, we have one last special value to check, and that is k equals negative 3. So let's replace. The first row again stays the same, as there is no k. The second row 0, 1, negative 1, 1. And the third row 0, 0, 0. 2 minus negative 3 is 2 plus 3, positive 5. And if you notice now there's something different happening. The bottom row says 0x plus 0y plus 0z. No matter how you choose x, y, and z, the result is 0. So the left-hand side is 0. That has to equal 5. This is clearly not possible, and so the system is inconsistent. Therefore, there is no solution. And now we're done. So we can write, finally, a proper conclusion. Let's rewrite it up here. So this is the original linear system for every value of k. I'll write a circle with a slash to say no solution. This is the empty set, no solution. I'll write 1 for a unique solution. And I'll write infinity for infinitely many solutions. So let's go back. We always, as we have seen in this case, handle the case when we have a unique solution. And this was, as long as alpha was not 0, as long as k was not 2, and not negative 3. So how do we write this? Well, we're saying k can be a member of the real numbers, except for minus the two options of 2 and negative 3. And for the two exceptions, when k was 2, we had an infinite number of solutions. So we have infinitely many solutions for a single value of k, which equals 2. And we found that when k was equal to negative 3, the system was inconsistent, therefore we had no solution. And we're done. So for every value of k in the real numbers except for 2 and negative 3, the system has a unique solution. There are no solution the one time when k equals negative 3, and there are infinitely many solutions the one time when k equals 2. And that's it.